For vehicles on inclined planes, we have to also consider the location of the center of gravity. In this case, here is a center of gravity, and we're looking for how much friction does it take to keep this thing parked on this steep hill. In this case, we have the car is 1,500 kilograms. It's on a steep hill. It only has rear brakes, only has rear parking brakes. The front brakes are free to roll. In other words, no brakes at all on the front. Parking brake only applies on the rear. How do we get there? All right, let's see what we're looking for. We want to find the minimum coefficient of friction to keep it from slipping down the hill. In this case, the tip scenario doesn't really apply. We're not going to see this car flip over backwards, if you will. So when you see a car parked on a hill like this, we're only really worried about it being in a slip condition. So let's draw a Freebody diagram and see what we get. I'm going to draw two wheels here, and then a car that looks like this. And not a very nice looking car, but that's okay. It's got a center of gravity there, a normal force at A, and a normal force at B. The mg has an mg cosine theta and an mg sine theta. And then again, the force of friction is going to go in this case. All right, how do I get there? If I knew if this is the slip scenario, then I know that the force of friction is equal to mu b. But in this case, b is not equal to mg sine theta or mg cosine theta. It has a normal force that we have to calculate. So let's go ahead and use a moment equation to see if we can calculate the normal force at b in order to calculate that friction force. If it's slipping at b, I will sum the moments about a, which will allow me to solve for the normal force at b with one equation. So let's do that. Sum of the moments about A is equal to 0. In this case, I have minus mg cosine theta times the lever arm of 0.8. That's right here. This is my mg, and there's the lever arm, mg cosine theta. This is the lever arm about point A. Then I have mg sine theta, and it's got this lever arm, this lever arm right there of 0.4. It is also going in the negative direction. So that'd be minus mg sine theta, and its lever arm is, in this case, it is 0.4. Then I have b over here. B is pushing up, and it's going to be in the positive direction. It has this whole lever arm, and that looks like that is 2. So plus b times 2 is equal to 0. I should probably do that a little bit better. Plus b times 2.0 is equal to 0. Okay, I have a weight. I have 1,500 kilograms. So 1,500 times 9.81. And then I have 0.8 cos theta plus 0.4 sine theta. It just factored out the mg right there. Plus b times 2.0 is equal to 0. So here I can solve for b is equal to 6568 newtons. Now, once I know the normal force at b, I should be able to solve for the coefficient of friction required by summing the forces in the x direction. So the x direction is here, this is y. Sum of the forces in the x is equal to 0. So I'm going to go uphill as positive. So I'll have force of friction going up minus mg sine theta going down. Those are the only two forces in the x direction. This is going to be mu mg. I'm sorry. This is going to be mu times b, mu b, minus mg, which is going to be 1,500 times 9.81 times the sine of 30 degrees is equal to 0. I just solved for b. Plugging that into there, I can see that mu here then is equal to 1.12. That is the coefficient of friction required to park on a steep hill like that. Now you may ask, that's a pretty steep hill. You may also ask, is that a realistic coefficient of friction for a set of street tires? And in general, the answer to that is no. Most street tires do not have that high of a coefficient of friction. So you may have trouble staying put if you park your car on a steep hill like that and just put on a parking brake. If you had both A and B, both the front tires and the rear tires able to lock, then you might be able to make that. But just with rear tires, probably not. Well, here's another car on a hill, and in this one, instead of pointing uphill or pointing downhill like the previous automobile, this guy is parked sideways to the hill. And our question is, what is the greatest slope or the greatest angle that he can park on without something happening? And the two things that could happen would be he could either slip down the hill or he could tip. And the tipping scenario could happen, I suppose, if if you got this angle steep enough, he could tip over like this. So we're going to analyze the greatest angle for both of these guys. We have a coefficient of friction of 0.4 of the tires. So in this case, because all of the tires have the same coefficient of friction, for the slip scenario, all you have to do is just consider one normal force. You don't have to consider normal forces at both A and B. For the tip rotation, or for the tip scenario, it rotates at A and then B goes to 0. So we can analyze either one of them first. Let's do the tip scenario first. So I'll draw a little free body diagram here of my car. It's got an mg, so I'm going to say this is mg sine theta, mg cosine theta. Got a normal force and a friction force. I'll say this is A and force of friction. So we're going to do the tip scenario first. At tip, it will rotate at A and B goes to 0. So in that case, we just sum the moments about the point of rotation. So what have I got? Got mg sine theta, and I have a lever arm. This mg sine theta is right there, the lever arm of 2.5. So that'll be positive mg sine theta, lever arm of 2.5. Now, mg cosine theta is also a factor, and it's got half the width, or half of the track here, and that looks like it's also 2.5. Pretty small car, it's only got a 5 feet track here, but this is minus mg cosine theta times 2.5. And those are the only forces causing rotation about point A, because B has gone to 0 up here, so there's no force right there. So that's equal to 0. And we can solve this for angle theta. And I'll just say we've got sine theta is equal over cosine theta is equal to mg 2.5 over mg times 2.5. That's equal to 1, which is equal to the tangent of theta. Now we just take the inverse tan of that, and you can get theta here is equal to 45 degrees, and that is the tipping angle, 45 degrees. How about the slip? The slip condition happens. Let's draw another free body diagram. So I'll get a little free body diagram here. In this case, again, the normal force can be anywhere. It doesn't have to be at the point of rotation. It's just normal like this. There's going to be a force of friction that applies to both tires. You're going to have mg sine theta and mg cosine theta, the normal force. Now, we can do this. We can say that we know that the normal here is equal to mg cosine theta. The force of friction then would be equal to mu mg cosine theta. So sum of the forces in the x is equal to 0. I have the force of friction minus mg sine theta is equal to 0. So I'll just put all those in there. Mu mg cosine theta minus mg sine theta equals 0. I have a mu of 0.4, so I'm just going to put that in there, 0.4. Now, here's another observation, is that 0.4, oops, sorry about that, 0.4 here is equal to mg sine theta over mg cosine theta. Mg again cancels, and so that's equal to tangent theta. So in this case, the theta for slip is equal to 21.8. You can also do this with the friction angle. We talked about that at the beginning of our friction scenario. So whenever you see a slip scenario like this, all you have to do is just say that mu, using the friction angle concept, and that we called the friction angle phi, we're going to say that phi is equal to the inverse tan of mu. And we can find that easily. In this case, the inverse tan of 0.4, that's equal to 21.8 degrees. So you can go quickly if you recognize that the friction angle concept applies. Well, here's another friction scenario. We have a loader pushing a log up the hill. What do we do with this? What we're looking for is, can the loader push it up the hill? Does it have the capability? Is there enough friction? We're going to assume that the torque of the loader is enough that it can push, that it's not going to be torque limited. It will be friction limited. I guess that's what we're trying to say. Now, there's more than one way of doing this, but if you break this up into two parts, there's a loader free body diagram and log free body diagram, and that's what I've done here. And what I did was I tried to figure out how much force does it take to push the log up the hill. What is the pushing force that happens right there at the interface between the loader and the log? And if I sum the forces in the x here, some of the forces in the y, we got normals equal to mg cosine theta. Some of the forces in the x, I can find out the requirement to push it up the hill is going to be 366.32 pounds. That's a 10-degree hill. Now what I want to do is analyze the loader and see if it has the capability of generating 366 pounds at this point where the tip of the shovel, if you will, is applied. So let's just look at that. Let's draw the free body diagram, which I've done, and let me just help you walk through it. It's got an mg sine theta and mg cosine theta. It's got a normal force at A, a normal force at B. P here has a little bit of a lever arm, and if you look right there, there's the lever arm for P. It's pushing back right there on the tip of the shovel, and it has that lever arm. What we're looking for is, do I have enough friction? I have a coefficient of friction which is given as 0.8. Looks like I missed that. There is a coefficient of friction between the rear tires of the tractor and the ground of 0.8. And so all I have to do is sum of the forces in the x direction and see what I get. Sum of the forces in the x. I have this force of friction, which is going to be, once I find out that normal force at A, I can say the force of friction here is mu A minus mg sine theta minus P is equal to 0. And I can find out what A is as a function of P. Now, if I want to find out that normal force at A, what we've done before is sum of the moments about B, and I can find out the normal force at A. So let's do that. Sum of the moments about B, got mg sine theta times this lever arm, which is given right there is 2.5. Mg cosine theta will have this lever arm, which is 3. A has this lever arm, which is 10. So minus A times 10. Plus P. P has this lever arm. P is going to be equal to 1.25. All right, So what I'm trying to do is solve this for P and find out how much P I can generate given a impending slip scenario. So all I did was, I know all of these things. I know mg, I know sine, mg and cosine. I know a as a function of p, plug that in here, and then solve this for p, and I can find out that I get 866 pounds available. I needed 366 to push the log. Available is 866. So yes, it can definitely move the log with plenty of force to spare. And again, that's not the only way of doing this type of problem. There are other methods, other approaches. This is just the one I chose to use.